All right, everybody, hello, and welcome to our next topic, which is t-tests. So t-tests are very close in relation to the z-tests that we learned about during hypothesis testing, but they serve a different function and, truthfully, a more practical function. The main difference that we're going to learn about here with a t-test to a z-test is a t-test is still comparing either one sample to another sample or a sample to a population. However, it differs from a z-test in that we don't assume as much about the population that we're drawing from. So that is an introduction. Just goes to show that this is a more practical and more widely used test. And t-tests have a few different forms, and we're going to learn about one first, which is called the independent samples t-test. All right, so we've learned the term independent samples before, right? Independent means that one thing doesn't affect the other. So in this case, we're taking two samples that don't affect each other and comparing them using what we call the t-statistic. And I do like to include a little bit of history here with this particular t-test because this has an interesting origin. This man here served as the head brewer at Guinness, and he had thought to himself, hey, we have multiple fields of hops that we use to brew beer, but they wanted to cut back. They wanted to get rid of one of their two large fields of crops. But he wanted to get rid of the one that was yielding less of the crop. So he came up with an elegant little statistic to determine, using probability, like we learned last time, to determine if one field was consistently producing significantly more than the other. So that's what we're going to learn to do here, is compare two independent samples to each other using what we call the t-distribution, which is another probability distribution. All right, so we're going to start here. We have two other types of t-tests that we'll be learning about, but we will start with the independent samples t-test. So when do we use it? We use it when we have two groups. And oftentimes in psychology, what this means is having an experimental and a control group. So take clinical drug trials, for example. We have a group that's receiving the drug and a group that is not receiving the drug, right? Or in this case, we're talking in terms of treatment. Or we can just compare two things, right? It often depends on the direction of our hypothesis or our prediction. But this is generally when we use an independent samples t-test. So what is an independent samples t-test? We use this when the population variance is unknown. So remember that variance is part of variability that we ultimately use standard deviation to determine. But in this case, in this calculation, we use variance again because variance is a larger measure of differences in scores across a data set. But what a t-test assumes, and what the t-distribution assumes, is that we don't know the population variance, or we don't know the standard deviation of the population. And as we mentioned before with sampling, if we know everything there is to know about a population, then there's really not much use in us calculating sample statistics from that population. So we have a comparison distribution called the t-distribution. It looks a lot like the z-distribution. It's a normal curve in which we have t-values along the curve that indicate different probabilities of occurrence on that curve. So we will get to that in just a moment. But this is also a hypothesis test. This is going to run very similarly to a z-test. In fact, one of our types of t-tests is almost identical to z-tests. But we still need hypotheses. Okay, let me get my head out of the way. We have hypotheses for this specific type of prediction when we're comparing two independent samples. And much like our previous hypotheses, our null hypothesis is going to be that there is no difference between the two groups that we're observing. The alternative will be that there is a difference, right? And it might be that one group is greater than the other or not. So here I have the mathematical hypotheses. So we have the Greek letter mu. So the mu of group 1 is equal to the mu of group 2. And remember, even though we're investigating using samples, we're still ultimately making inferences back to the population. We want to know if our samples are representative or fit into what is already assumed about the population. So that is why we use the Greek letter mu here in our hypotheses. All right, so on to the formula here and a set of assumptions that we have when we're working with t-statistics. Here's our formula. We will have two samples, right, as evidenced by the independent samples. Here they are. We have x bar 1 and x bar 2. We're going to have variance from the samples and sample size. So notice that there's actually no population parameters included in this calculation. We're only using sample statistics. This is what makes a t-test way more practical than, say, a z-test, because again, if we know everything about the population, then we won't be interested in running sample statistics from that population. So we have steps for our hypothesis testing. We have our hypotheses first. We need to do things like determine the cutoff score, our significance cutoff. We need to calculate a t and then decide, make a decision on which hypothesis seems to have evidence to support it. So the same 4 steps we were using before, we will use again here. One slight difference that we have here between the z-test and a t-test is how we look up our cutoff scores. And handily, we have a t-table, much like our z-table, in which psychologists, statisticians, have calculated the area under a normal curve at any given t value. So we're going to use alpha levels and significance levels again. That'll be given to you in the question as it has been previously. Then you'll be going to this t-table to determine what t-score we need to exceed in order to achieve statistical significance. So let's go ahead and put this into action. All right, I think this is best done as examples here. So let's go ahead and get into one. All right, so let's say we want to make a comparison between 2 sample groups. All right, let's say that we want to compare individuals who have faced either low adversity or high adversity. Oh, getting ahead of myself. High adversity. All right, so we're going to end up with 2 sample means for each of these. And what is it that we're going to compare across these 2 groups? Let's compare well-being, all right? And what is adversity? Adversity is basically hardship, any hardship anyone has endured. So maybe your hypothesis here is people that have faced low adversity and people that have faced high adversity will have a different level of well-being. So we're going to say different level, right? But not that one is going to be greater than or less than the other. We're just going to predict that there's a difference. This is a common question in psychology, which is about resilience. It seems as though some people that face hardship end up with a large body of resilience to face other potential hardships. So it's kind of a blurry question, right? There's no obvious direction we might predict between these 2 groups. But let's say that you grab a sample. All right, so we're going to have variance. I'm going to report variance and the N of each of these groups. So we'll have 3 different statistics for group 1, and then we'll also have them down here for group 2. I'm just noting them using different subscripts. So let's say we take a sample. We'll start with a small sample here. Let's say we take 7 people who have faced low adversity. You've operationally defined this for your study, and 7 people that have faced high adversity in their life. So we get a mean or an average here for well-being, and let's say we have well-being scores that look something like this. And remember, these scores don't mean much until we apply things like variance to them. So let's go ahead and give variance for these values as well. And let's say that we want to test if there's a difference between these 2 independent samples at an alpha level of 0.05. All right, we'll stick with our classic 0.05 alpha level. All right, so let's go ahead and think about our hypothesis testing steps. Let's get our 1, 2, 3, 4 steps going over here. We have our hypotheses we'll need to get in here first. Then we'll need to find a cutoff score. I'll show you how to do that using the t-table. Then we will calculate and decide and see if there's a significant difference between these 2 groups. All right, so let's start with those hypotheses. All right, so step 1 here will be to get these hypotheses in order. Okay, so the null, all right, as always with the null hypothesis, is just that there's no difference. So we'll say something like adversity has no effect. All right, I'm abbreviating a bit here, but what we mean here is no effect on well-being. So in this case, we're saying the people that belong to a population of low adversity are going to be equal to the population of those that have faced high adversity. Let's go ahead and write out our alternative too. So we'll say that adversity does have an effect. Does have an effect. So has an effect. And we'll say that these 2 things are not equal because we think that adversity is going to affect ultimate well-being. Okay, so let's also go ahead and move into getting our cutoff score. And before we do, I want to mention what we need to find a cutoff score for a t-test, all right? So we need an alpha level, that's given to us here. We need the number of tails in the question, and in this case, if we go ahead and draw in a curve, remember the giveaway for number of tails is right here. If we're saying does not equal, that means that we don't have a specific direction that we're predicting this is going to go. So that would make this a two-tailed test, all right? So we'll have two critical regions, one on each side. All right, so we need the alpha level, we need the number of tails, and we need one more thing. We need degrees of freedom. Right, it's been a little while since we talked about degrees of freedom. We talked about degrees of freedom back when we were doing variance. Degrees of freedom is a value that indicates if you've given any values in your dataset freedom to vary. It's a little bit abstract, but the way I like to think about it is giving the numbers a little bit of wiggle room. It's basically accepting that these samples here are imperfect. We're saying, hey, we got these samples, but they might not be exactly correct, right? There could be a bit more variance to these than is indicated by this sample. So degrees of freedom is a mathematical way to kind of control for that. So we have a means of calculating degrees of freedom here. We do something that looks like this. Degrees of freedom is calculated by getting the N1 and the N2, all right, those that are given up here, and then we're subtracting K, all right, and K is a new value for us. And what is K? K is equal to the number of groups that we have. So when we're doing an independent samples t-test, we're comparing two samples, right, or two groups. This is evidenced by how many N's we have. So we're always going to have two groups for an independent samples t-test, but just keep this in mind, keep K in mind for when we move into a further topic called ANOVAs, or analysis of variance. We use K in that calculation as well. So if we go ahead and get the degrees of freedom here, we have an N of 7 plus an N of 7 minus 2 gives us a degrees of freedom of 12, right? So we have our tails, right? This is a two-tailed test. We have our degrees of freedom and we have our alpha level. So the next thing we want to do is go to the T table, the trusty T table, which is a little bit different than the Z table, but also similar in its own right here. I would say this is simpler than the Z table as well because we only need a few things. We need the number of tails. If you take a look at the top column, or the top row here rather, we have a distinction between one-tailed tests and two-tailed tests, and there are two distinct columns on this table that we need to consider. So on the left we have one-tailed tests, on the right we have two-tailed tests, and if you look just beneath those curves, we have some alpha levels listed off. We have 0.10, 0.05, 0.01. Remember, we will not be using 0.10, and to be honest with you, I'm not sure why they have it here. That's not a very widely used alpha level at all. So we're going to ignore it because that's more error than we're willing to accept in our statistics here. Then if you look all the way to the left on this table, you see a column for degrees of freedom listed from 1, and we move on up all the way until 100. And then we hit a kind of infinity. If we have more than 100, we hit an infinity here, meaning that there's going to be a negligible difference when we increase or go over 100 for our sample size. This is related to statistical power, which we touched on in hypothesis testing. The larger our sample sizes, the more likely we are to find significant effects. It makes our significance values lesser and easier to support using statistics. So that's just a sort of law of large numbers, central limit theorem type of idea. But we're not working with a sample that large. We have only 12 degrees of freedom. And we also determined that this is a two-tailed test, and we know that this is at an alpha of 0.05. So I'm going to first of all start in the very right column that says two-tailed tests, and then I'm going to move down to those three alpha values. I need 0.05, which is in the middle. So then moving down from there, I would move down to 12 on this particular table. And if you move down to 12, you'll see a value that is 2.179. 2.179. I'm going to go ahead and write that down. So we have negative 2.179 and then positive 2.179. So hopefully you see how this is pretty similar to our z-test. Now what we need to do is calculate t using that formula and see if r value exceeds these values. But let me point out something else before we really get going on calculating. This x bar 1 and x bar 2, these are labeled for REs, but keep in mind that these are kind of arbitrary labels, right? They could be reversed. We could have called the high adversity group Group 1 and the low adversity group Group 2. So when we find a t value here, we're going to pay attention to the magnitude of the t rather than the sign of the t. So we're going to have more examples of this as we go, but just keep that in mind. All right, so let's go ahead and get a fresh slide here and let's do our t calculation. All right, this is our third step in the hypothesis test. So t is equal to x bar 1 minus x bar 2. We're going to put that all over a big square root. Don't forget the square root. That's an easy thing to forget. Let's go ahead and get this in here. All right, this is the formula we're using. And if we plug in the values from this question, all right, we have a mean of 41 minus a mean of 48 all over 50 over 7 plus 62 over 7. All right, and if we do this math, it works out quite nicely. All right, we got negative 7 up top, and then we end up with a square root of 16 in the bottom. And please do make sure you're calculating along with me, making sure you can get the same thing, that you're following your order of operations down here. And then we get a t value. If we kind of carry the rest of this out, right, we get negative 7 over 4, which gives us something like negative 1.75. All right, this is our t value. Okay, so let's go ahead and take it back to our curve here. Is 1.75 in our critical regions? I don't think so, right? It'll be somewhere over here. So remember when we find something in here, this is in support of the null hypothesis, because remember that this curve is equal to this, right? Adversity having no effect. So this is where it's a little different from the z-distribution, right? On the z-distribution, we have the population mean in the center, and that's what we're representing. But what we're doing here is actually comparing the central tendency and variance of two independent samples and seeing the magnitude of their differences. What this is saying is these two groups don't seem to differ very much. So this would mean that we retain the null hypothesis. All right, so we would retain the null. And then what does that mean? We would say that it doesn't seem that low or high adversity ultimately has an effect on well-being based on this sample. All right. So of course we talked about type 1 and type 2 errors when we went over hypothesis testing. It's possible that we made an error, and it's specifically possible because we have very small sample size here, right? This is kind of for demonstration's sake, but we would never take a sample size like this at face value, right? It's pretty small of a sample size, and we've included that sample size as a consideration using degrees of freedom in finding our cutoff score. But otherwise, this is about the same procedure as retaining or rejecting the null hypothesis as we were doing in the z-test. We just take our calculated t statistic, like we have here, and compare it to our cutoff scores. But remember, if we switched these values, right, and we had something like 48 minus 41, this would have been a positive 7, this would have been a positive 1.75. But if we move over here, it won't make any difference to the ultimate decision, all right? So just keep that in mind. It can be a little bit confusing, but that's why we set up our hypotheses ahead of time, because then we just know which one of these hypotheses will be supported at the end of the day here. Right, and if we did find a significant finding, let's say that we find a significant finding over here and we decide, hey, they are significantly different, what we would do is we would go back to these original means and say, well, this group was higher in well-being, right? So we'd say adversity has a significant effect, and those in high adversity have higher well-being. All right, that was a bit of information for us, wasn't it? Let's try another independent samples t-test. Let's try one more while we're at it here. Let's say we want to compare sleep. We want to see if sleep has an impact on cognitive aptitude. All right, cognitive aptitude. All right, so we know that sleep's important, right? Hopefully we do. I have my own little soapbox about sleep, all right? Here it is, all right? Never brag about how little sleep you're getting, That's not good. You're basically bragging about not being nice to your brain. All right, and there's a big culture in academia and in grad school where you need to be so busy and you need to be working all of the time. You need to not be sleeping enough, and that's just not true. If you want to be productive and you want to be hardworking, you should make sure you're getting enough sleep. All right, soapbox is over. So here we go. Let's say we're comparing cognitive aptitude scores on a test or on a measure to see if people who get 4 hours of sleep perform worse than those who get 8 hours of sleep. All right, so there's already some direction to this test. We're saying, hey, we think the people that get 4 hours are going to do worse on this particular test. So I'll show you how we work that out when we go to our decision making. So let me go ahead and get some values in here. All right, we need some variance. We have smaller values here. So of course we're going to have smaller variance. That's okay because variance scales with whatever metric we're using. And let's also keep it pretty small here. So sample size of 8 for each of these groups. So let's go ahead and think about our 4 hypothesis testing steps. We have our null and alternative hypothesis, we have our cutoff scores, we need to calculate, and we need to decide. All right, so let's go ahead and start with our HOHA. All right, we always start with the HOHA. Okay, so the null hypothesis is a little bit boring here, right? It's always really going to be the same. So we're just going to say here that sleep has no effect on cognitive aptitude. All right, I'll abbreviate here. So sleep has no effect on cognitive aptitude, so both of these groups are going to perform the same, right, or fit into the same distribution. But the alternative would be that sleep improves. All right, sleep improves our cognition. All right, so we would do something as follows, right? If this is group 1 and this is group 2, we would say, okay, we expect that group 2 is going to do better than group 1. All right, and now we know how many tails this test has, right? Remember, if there's a direction here, it means we only have one tail. And this is where t-tests get a little bit tricky. They get a little tricky because we're looking at the magnitude of the t rather than the sign of the t. So we'll go ahead and flush this out here in a minute. Let me go ahead and get us a new slide too. Let's just keep it nice and clean here. So we need cutoff scores, right? And we only need them in one direction, okay? But remember, the order of the groups is arbitrary. We labeled group 1 and group 2 just to have labels for ourselves, right? So this is a one-tailed test, and you can technically put that one tail in either tail. And I'll show you why. But what I'm going to do is, this is just for visualization's sake, okay? Just for visualization's sake. I'm going to go ahead and put... Well, we don't have our cutoff score yet. I'll put our cutoff score here, all right? Well, I'll put our shaded region over here. But when we put in our t over here, we're gonna also know in our minds that a negative t of the same value will also be significant for this particular circumstance. So I know that might be a little confusing, but let me just show you. All right, let's test this at an alpha of 0.05. All right, so this is one piece that we need in order to figure out our cutoff score. We also need the number of tails. This is one tail. And then we need degrees of freedom. So remember, degrees of freedom looks something like n1 plus n2 minus 2. So in this case, we have 8 in each group minus 2. So we end up with something like 14. All right, so 14 degrees of freedom, alpha of 0.05 on a one-tailed test. Let's go look at the table and see what type of cutoff score we're working with. So we're in the leftmost set of columns now, right under one-tailed test. We're in that center column that says 0.05, and then we're going to scroll down to 14. All right, to 14, and there's a value there that is 1.762. 1.762. So I'll hop back over to the whiteboard and I will put that value right here, 1.762. But here's where we differ a little bit from z-tests. What I like to do is instead of, I like to do this for visualization's sake, have this curve here. But to be practical, and in fact I'll put it up here in a different color so we don't lose track of it. I like to write down something called the t-critical. Remember, these are our critical regions. So we want to know what t-value marks our critical regions. Well, in this case, we just need to exceed the magnitude of 1.762. Right, remember, if we switched our x bars, right, x bar 1 and x bar 2, it could be just as well that we're looking for a negative t. So that is arbitrary, but what is not arbitrary is exceeding the magnitude or the absolute value of this critical t value here. All right, so let's go ahead and calculate then. Let's get our t. So remember, our formula looks like this, right? We're comparing both of those independent means and their variance, all right, over their n. All right, so it's going to look something like this. Get all those values in here, 4.57 over 8 plus 6.57 over 8. If we do a little bit of math here, we get something like this, and we get a t value that looks something like this, all right, 0.847. So if we go ahead and put this on our curve here, it's not in our critical region, right? So notice again that we have a positive value here, so this is where that value would go. But even if it were to go over here, right, and maybe we had set up our critical region to be over here, it wouldn't be over there either. Okay, that's why we just look for magnitude of effect when it comes to t. All right, so what does that mean? If we are not in the critical region, we need to retain the null. All right, we need to retain the null. All right, and what does that mean? It seems that sleep has no effect on this particular cognitive aptitude test. All right, I think we're doing pretty good so far, aren't we? Hopefully this rings a bell, right? Hopefully this seems similar to our z-test, and the next type of t-test that we're going to do is even more similar. So let's go ahead and take a look at that. Okay, so here we are talking about significance for t. This is going to persist for the next test we're going to learn about, though we do find the cutoff score in a slightly different way. So now we're going to try out what we call a one-sample t-test. So a one-sample t-test is almost identical to a z-test. The only difference is the population standard deviation being unknown, and instead we rely on the standard deviation from our sample. Again, this is much more practical than making assumptions about the population because we're using real data from real samples. So this is common when we use a sampling distribution or assumptions about the population mean, which is most often the case, because remember, having every example member of the group you're interested in making a statement about is hard, right? It's hard to gather data on everybody that you're interested in gathering data about, unless it's a very small group. So that's the formula, and then now we have our hypotheses, all right? And our hypotheses are going to be much like our z-test hypotheses, right? So the null is going to be that we fit into, right, or mu is equal to the given mean, that we're just going to fit right into that population, or the mu or the population mean of our sample is actually going to be different. So again, conceptually what this means is that we think that our sample might belong to a different population than we're considering for a particular test. So let's go ahead and give this a try as well. The procedure is very similar, just a little different in the information that is given. Let's go ahead and hop back over to the whiteboard. Let's get a new slide. And let's talk about one sample t-tests. So one sample being compared to a population. So let's go ahead and try this. All right, so, you know, we try not to talk about it, right? But 2020 has provided us with some changes, right? Some of them psychological. So we're going to talk about quarantine dream intensity. All right, we've maybe heard this or maybe not, but there's been a rumor going around that people have been having more intense dreams when they were in quarantine or in lockdown. All right, so we're going to play with some data to try and test a hypothesis like this. So we're going to test the hypothesis specifically that dreams are more intense, right? More intensity to our dreams during quarantine, all right? So let's say that we have some information, right? And this will all be provided to you in the question. Let's say that we know that the average intensity for dreams on a certain dream scale is 100. And let's say that we get a sample, all right, of 30 people. A sample of people who are being quarantined or were quarantined to report how intense their dreams were at that time. And on this particular scale, they got a mean of 140 with a standard deviation equal to 20. And let's go ahead and test this at an alpha level of 0.01. All right, 0.01. So let's go ahead and start with our hypotheses. Okay, if we have our four, I'll put them here for good measure. You know, I love to have them around. Our four hypothesis testing steps. So we have our hypotheses, we have cutoff values, we're going to calculate, and we're going to decide. All right, so let's start with those hypotheses. So the first one would be that dreams are not more intense, right? Dreams are not more intense, or that quarantine has no effect on dreams. Hopefully you've noticed that there's a change in vocabulary for these, but always the same meaning. The same meaning being that there is no difference in what we're measuring. So dreams are not more intense, okay? And the alternative would be that they are, all right? Dreams are more intense. And of course we could flush this out a bit more, but I'll leave it abbreviated. So the hypothesis here would just be that we're going to fall in line with what's already known about the population, right? If we already know that average dream intensity on the scale is 100, then maybe quarantine dreams will just fall into that and there will be no difference. But we're predicting that there might be a difference, right? That maybe it's going to be of greater intensity. And when we take a look at this sample mean, we might say, hey, that seems a bit higher than 100, but we'll let the math decide if there's a significant difference between these values. All right, so let's go ahead and get our cutoff score going too. Let's get a curve here. This is a one-tailed test as evidenced by this greater than or less than sign in our hypothesis. So we're going to do the same thing and just represent one tail here on this curve. We're going to test at an alpha of 0.01. So 0.01, one tail. And then we need degrees of freedom. So degrees of freedom is actually moving back in a more familiar direction. In this case, we're just doing n-1 because we only have one sample that we're worried about, or only one n, right? So the dead giveaway for how many groups you have is how many n's you have. So the reason we did n1 plus n2 minus 2 is we're subtracting 1 from each n. But if you remember back to when we calculated variance, this is what we used in the denominator for variance. So this is a standard calculation for degrees of freedom. So in this case, we're taking 30 minus 1 is equal to 29. And these are the components that we need, right? Remember, we need alpha, we need the number of tails, and we need degrees of freedom to head over to our t-table. So let's head back over to our t-table and use this information. All right, so we have a one-tailed test, so we're on the left-hand side of this particular table. And we're testing at an alpha level of 0.01. So when you look at those three alpha levels, we have 0.1, 0.05, and 0.01. We're in that last 0.01 column on the one-tailed test side. And we have 29 degrees of freedom. So we're going to scroll down to 29 degrees of freedom. We find a value like 2.462. 2.462. Let me write that down. Let me get a different color too. 2.462. All right, that's the t-value that we need to exceed in order to say that there's a significant difference in our sample compared to the population. All right, so let's get a new slide here, and let's go ahead and try out that new formula. So while this formula is new, it should feel familiar. The only thing that's different here is this S from our Z. Z had sigma, this has S. So instead of pulling our standard deviation from the population like we did before, we're pulling it from the sample. And again, this is much more practical. It's more likely that we have information from our sample rather than from the population. So let's go ahead and plug in all of our values here. All right, the quarantine dreamers had intensity of 140, where normally average was at 100. So we're going to see if this difference is due to chance or if there really seems to be a difference in dream intensity based on this data. All right, so we just carry on with our math here, and we get something like 10.96. That's a pretty big t-value, right? Remember, this isn't exactly like z. It doesn't mean that we need to find a t between, say, -3 and +3 like we had to do for our z's. but we can still remark on a large t, right? This is a big t value. So if we take this back, is this in our critical region? It most definitely is, right? This is a very big value. So remember, if we switched these for the calculation, this would have been negative. And it doesn't mean that this wouldn't have been significant, because again, we should think of our cutoff score as something like a t critical. All right, for us to be in the critical region, we need to exceed the absolute value of 2.462, which we have done here. So remember, if we land in this critical region, the probability of that happening was low, in fact, less than 1%. And with a t-value this big, it was probably less than 0.0000001%, right? It's very, very unlikely. So when the p is low, right, when the probability of this happening is low, you already know what it is, right? The hoe has to go. We have some evidence to suggest that the alternative is true or more accurate, right? And remember, we're not saying it is true, but we're saying we have some evidence to suggest that maybe it is, right? Maybe we do have evidence to support this. All right, let's go ahead and try one more of these one sample t-tests. And this is one of my very favorite examples because it's based in a real study that sounds almost too ridiculous to be real. It's about injecting caffeine into polar bears to see if they migrate faster. All right, to see if they migrate faster. Again, sounds ridiculous, but science stops at no bounds. So let's go ahead and think about this one here. So let's say that we have two hypotheses, right, as we always do. And the first one will be along the lines of caffeine will not impact migration. All right, keep it abbreviated here. And then let's say maybe we're concerned that caffeine might not affect polar bears at all, right? Maybe there are some species that aren't affected by caffeine. So let's say that our prediction is just that caffeine will have an impact. All right, not that it's going to increase migration, but just that it will have an impact, right? So let's get some values in here. Let's say that on average, polar bears migrate 100 miles, and we inject 25 of them with caffeine, and we find that after we inject them with caffeine over the course of a few days, they migrate 150 miles with a standard deviation of 9. So this is our first step in the hypothesis testing. Let's do our second, which is our cutoff score. All right, so this is a two-tailed test because our null hypothesis will be that we are the same here. The alternative will just be that they're different than what we already know about them. All right, so a two-tailed test, and let's test this at an alpha of 0.05. So remember, I will always give you the alpha, and I'm also always going to give you these values here. All right, so as we go through these examples, and I'm just bringing up information as we go, when you take a look at, say, the homework assignment that has to do with these, you'll see that all this information is readily available for you. All right, so we got a two-tailed test at an alpha of 0.05, and we need degrees of freedom. All right, we need degrees of freedom. So let's go ahead and do that. So degrees of freedom is the same here, just n minus 1. We have an n of 25 minus 1 gives us 24. All right, so we have two tails, an alpha of 0.05 and 24 degrees of freedom. So if we hop over to our table here, we are over in the two-tailed test column at an alpha of 0.05, and we need to go down to 24 for degrees of freedom. And we find a value like 2.064. 2.064. Let's go ahead and put that on our curve here. All right, negative or positive. And remember, we can always write this down as our t critical is equal to plus or minus 2.064. Remember, we're just looking for a magnitude of difference. Using the curve here is just for our visualization's sake. All right, so let's go ahead and calculate the t here. We have x bar minus mu over the standard deviation of the sample over the square root of n. So we have a difference up top here, 150 minus 100 all over that standard deviation over the square root of n. And we end up with something like this. And my goodness, this is a pretty large t we find ourselves with here. 27.78. So remember, a large t shouldn't scare us off completely. Okay, this is not as crazy as maybe a z of 27 is. But a large t is still a large t. If you look at the t table, we don't have any cutoff scores that exceed about 3, about 2.5, 3, unless we're working with almost a non-existent sample. So it's nothing to scoff at, is what I'll say. Instead, a t this large is meaningful, right? So if we go back over here, does that fall in a critical region? I think it most certainly does. And I don't know if I need to say it again, but the probability of this happening was pretty low. That means that the null has to go. That means that we reject the null, and that we have evidence that this is true, that caffeine impacts migration of polar bears. So what we would also want to consider is if we wanted to make a more strong conclusion about this, someone might ask you, okay, well, it impacted it, but in what direction? That's when you would go ahead and take a look at these means. You would say, well, this mean is larger. So after they got the caffeine, they migrated further. So you could say something like caffeine had a positive impact, right, on polar bear migration. Okay. All right, we are doing just great so far, aren't we? We're just moving right through t-tests. But we have one more t-test to learn, all right? One more t-test to learn. So let's give that one a try as well. This is a counterpart to independent samples t-test because this is a dependent samples t-test, or something that we call a paired samples t-test. So this one has its own set of considerations, but it has this interesting little formula here. And it's specific to when you're measuring the same individuals twice. In research methods, we would call this a within subjects design, in which we're testing people before and after some event. And we're looking at the scores that are different or difference across time. So we'll do an example of this. And the statistics are going to be reported to you in this way. You're going to get a mean of the different scores, standard deviation of the different scores, and an n, or the sample size of the question at hand. So we have a few other considerations with this, one being how we write the hypotheses. These have a unique set of hypotheses because we're comparing before and after a given event, all right? So the null hypothesis is that there's no difference before and after an event occurs, and the alternative hypothesis is that there is a difference before and after some event occurs. And just like our other hypotheses, it can just be that there's a difference before and after, or that there's a specific direction of that prediction. So let's go ahead and give one of these a try. We'll just do one of these. All right, so let's say that we're studying an anti-hunger. Let's see, an anti-hunger weight loss pill. All right. Not saying this is a good thing, all right? A lot of these medications can be a little bit predatory, right? But no less, they're being made, right? And clinical trials need to be done in order to see their effectiveness, all right? So we're going to test out these pills before and after somebody takes them, all right? So we're going to test before and after measures of hunger. All right, please mind my handwriting. Measures of hunger in the same, all right, keyword, in the same people, right, in the same people. So we're going to get a sample equal to 10. We'll test this at an alpha of 0.05, all right? So let's go ahead and give this a little bit of thought here, and let's just set up our hypotheses before I even give us the data. All right, so we're going to want to do our 4 steps. All right, null and alternative hypothesis, cutoff scores, calculate, and decide. All right, so let's do our hypotheses. All right, so the null will be that there is no difference in hunger before and after. All right, so our hypothesis would look like this. The mean before will be equal to the mean after. And then the alternative will be that there is a difference, and specifically that it's anti-hunger, right? So hunger will decrease is the alternative. All right, so we're expecting hunger to be greater before than it is after. So again, I'm going through this verbally, but when you are, say, doing this on a quiz or doing this on a homework, this will all be written out for you to parse out. So let's go ahead then and move into finding our cutoff score for this. Let's get a curve going here. This is one tail because we have a direction in the hypothesis. All right, so we're looking over here. All right, so just like our other t-tests, we need our alpha level. We have an alpha of 0.05 here. We need degrees of freedom. So let me go ahead and put the, well, we're gonna need a new slide anyway. We already have our n here, so let's just go ahead and get our degrees of freedom. So degrees of freedom is n. All right, so n minus 1. We have 10 minus 1, so we have 9 degrees of freedom, one tail, and an alpha of 0.05. So let's go ahead and hop over to the table and figure out what cutoff score we're working with. We have a one-tailed test, alpha of 0.05 and 9 degrees of freedom. So if we look here, we have something like 1.833. Let me go ahead and write that down for us. 1.833. And remember, we can just think of this as t critical. We just need to surpass this in magnitude. All right, so let's go ahead and think about what type of data we're working with here. So here's our formula. And I'll tell you right now that for calculating this particular t-test, I'm going to give you all of these values. In fact, I could list these out for you right now, okay? So this is going to be something like 1.7. This is going to be something like 1.49. And then our n, of course, is 10. That was already given. But this type of data comes from something that looks like this. We call it a BAD table, all right? Before, after, and difference. So we would have the before hunger scores of people, all right? I won't list all of them here. Then we would have after scores after they take this specific pill, right? Have them rate their hunger. And then we would have difference scores here. Difference meaning 9 minus 7 is equal to 2. 10 minus 6 is equal to 4, all right? And we would go down the list. And then what we'd be doing is getting an average of these difference scores. So we'd add up all of these values divided by n. And we would do the same for calculating standard deviation of it as well. So that's where they come from. So let's go ahead and calculate. So in this case, t is equal to 1.7 all over 1.49 over the square root of 10. If we do a little math, we get something like 1.7 over what our square root of 10, 1.49 over something like 3.16. If we follow our order of operations, we end up getting a t-value like this, 3.61. Let's go ahead and over here and compare it to our scores. Is that over here in the critical region? It sure is. And again, we already know what to do. That means we have evidence to reject the null hypothesis, and we would suggest that the alternative is true, that hunger did decrease as a result of these pills. All right, so a bit of information we covered here today using a t-test, but the mechanics that we're using here are similar to z-tests and will be similar to what we learn next, which will be ANOVAs and confidence intervals. So if you're feeling a bit overwhelmed by these concepts, worry not. We have plenty of practice with all of these to come. So as always, let me know if you have any questions.